Okay, hello everyone, and welcome back to my YouTube channel, and welcome back to my session of short circuit analysis and some numerical examples that we are presenting in this series of videos. Okay, um, let me start about this problem. Okay, in this numerical example, we are working with this very basic problem, and there is a 50 hertz, 100 MVA, 18 kV turbogenerator, and is about to be connected for operation in a power station. Okay, the synchronous generator have the following reactance. Okay, as you can see over here, subtracient equal to positive, negative, and that is 20%. Then we have the zero sequence reactance, and is 5%. And this synchronous generator is connected at start connection, okay? But at the same time, it's equipped with a current limiting reactor connected at the neutral point, okay? The neutral point reactance is equal to 0.162 ohms, okay? Before the generator is connected to the power station, its terminal is adjusted to 16 kV. That is the terminal voltage when the machine is ready to be connected. But then there is a double line to ground fault. There is a double line to ground fault, okay? At terminals B and C, okay? And now the question is, okay, calculate the terminal, the initial symmetrical RMS current to ground and in the line B, okay? In this very specific case, we have a three-phase generator. Let's use the three-phase representation. We have here phase A, B, and C. Okay, you can imagine A, B, and C here, and those are the internal voltages. Okay, this is the neutral point. And then we have here a neutral reactance. Okay, this is the neutral reactance. However, the neutral reactance is 0.162 ohms. That means that this must be transferred into per unit values. Okay, sorry about my handwriting. Okay, and the fault that we are having here, you can see here that there is no problem here. The current is equal to 0. And then we have a double line, yes, and then going to ground, okay? And this is the current going here at the neutral point. This is V, and this one is C, okay? This is the situation, okay? Okay, I have been teaching for power system for probably many years, and more than years than the one that I want to remember. And this is a classical example for symmetrical component analysis, okay? Before I start the solution, I must say that this is one of the problems that I try to solve to show my students a different perspective and try to make my students think about what they are doing, okay? Um, It's very difficult when you are teaching engineering, because engineering is not memorizing formulas and having a set of equation in a paper and using those equations. Engineering is basically ingenious, is having the capacity to think outside the box, is the capacity to reflect and think about what you are doing. It's not just learning an equation, applying the equation, and and getting the numbers and get the job done. Okay. Yes, probably if you do that, probably okay, you can survive in your engineer life, but you will not be the good engineer that is creative, is reflecting, and is innovative is developing new ideas, okay? Okay, saying this is because what I will do now is I will solve this problem as a typical student will do, okay? And then what I will do is I will show you the way that I did, but not much people follow my idea, okay? Sorry for this very long introduction, okay? But I want to clarify this, the challenges of teaching engineering. Teaching engineering is not so easy, okay? Because it's not, again, it's not teaching formulas and how to put the numbers inside the formula. Is teaching how to think, and that is very, very complex, okay? Okay, this is a double line to ground fault, and um, all my students must remember the following, okay? If you are using a double line ground to fault, um, if you have the Thevenin model here for positive sequence, yes, this is the positive sequence. Let's say this is the positive sequence, equivalent model, okay? This is the negative sequence model, and this is the zero sequence model, okay? This is zero, this is negative sequence, okay? If we are working with a double line to ground fault and you memorize the formula, what you will do is this, okay? Put together the three networks in parallel and you will say that this current over here, that this is the positive sequence current. The positive sequence currents will be the voltage divided by the total impedance. In this case is this one positive sequence in series with the parallel of this. Okay, and then you have here negative sequence current, and then you have here the zero sequence current. Okay, I mean the classical way to solve this problem is, okay, you get the positive sequence applying this, then you calculate the negative sequence current. The negative sequence current is very simple. It's something like this. It's multiplying by the parallel of the negative and zero and dividing by the negative. And then you will obtain the zero sequence. The zero sequence current will be this one divided by 660 multiplied by this, and that's all, okay? And then when you have that, what you need to do is the following. Okay, I need the current IB0. I use the matrix A and multiply by the vector of and job done. Okay, here you will obtain the currents because you must remember that and this one is zero. Okay, because of course the condition. That is the mechanic way to do this. This is the way to do it if you are memorizing equations, okay? To be honest, I didn't spend time writing this down. What I did is I create a MATLAB live script and I prepared that solution. And this is what I will show you first, okay? What I have here is the numerical solution. You can download that from my GitHub, okay? And over here, what you need to see is the following, okay? Here, well, clear the screen and so on. This is the input data. You must remember that the nominal voltage is 18 kV. Yes, the nominal voltage is here. The terminal voltage previous to the fault is 16 kV. The other thing that you must remember is that subtracient positive and negative, all of them is 0.2 per unit. The other thing that you must remember is that the zero sequence impedance of the generator is 5%, 0.05 per unit. Then you must remember that the neutral reactance is 0.162 ohms. As a consequence, we need to change here calculating this in per unit, okay? Calculating the impedance base is extremely simple. You know the nominal voltage, you know the rate power. You calculate here the base impedance, okay? Calculating the base impedance, you can see that the base impedance is 0.324. And this is not per unit, this is ohms, okay? This is ohms, okay? Okay, then what we need to do is calculate the neutral reactance in per unit. Extremely simple. We divide the reactance that we calculate before, yes, the reactance that is given, 0.62 divided by the base, and we obtain here 0.05, okay? Simple. Next step, as you must remember, we are using a short circuit that is line-to-line ground, and we are using the mechanical, the typical mechanized way to do things, okay? You must remember that for line-to-line ground, we interconnect the three sequence network in parallel, and as consequence, the positive sequence current is calculated like the voltage previous to the fault divided by the positive sequence plus the parallel between the negative and zero sequence. That is what I am doing here, okay? We have here the zero sequence. Remember that when we have a neutral reactance, we need to multiply by 3. And then I have here the positive sequence, the zero sequence. I am calculating here the positive sequence current, okay? As you can see, that equation over there is matching what I was explaining. It's this equation over here, okay? Good. Then I calculate the negative sequence and the zero sequence currents, okay? You can see the equations over there, and those equations are coming from here, okay? It's the negative positive sequence multiplied by the parallel and divide by the negative, that is the negative sequence current. And for the zero sequence current is minus the positive sequence multiplied by the parallel, divide by the zero sequence. That is this equation over here. Next step is using symmetrical components and moving from the symmetrical components to ABC. That is something extremely simple, and that is what I am doing here. This is the vector for symmetrical components. This is the operator A. Then we are defining here the matrix A, and we are doing the operation, okay? The output that I am presenting here, you can see over here, this is the per unit current on phase B and phase B and phase C. Okay, what I will do now, let me go back to the visualizer. Okay, now here in the visualizer, what I will do is the following. Okay, the procedure that I am using right now is the line to line to ground fault, yes? And in this case, you can see that the current on phase A is 0 per unit. That was expected. Current for phase B is 4.4 periodic at 150 degree, okay? And then for phase C, we got the same magnitude, yes? And the phase angle is 30 degree, okay? All those quantities are per unit, okay? If we want the amps, what we need to do is multiply by the base current, okay? What we need to do is calculate the currents, the base current, okay? And that is what I am doing here. The base current is simple, is the rate power divided by square root times the nominal voltage, and we obtain here that the base current is 3.2 kiloamps. Yes, something like that. Yes. Let me take note here for my students. The base current is 3,207.501 amps. Okay. Then what I am doing is something simple. I am multiplying by the base and dividing by 1,000 because I want my results in kiloamps, okay? And what I am presenting here is basically the results in kiloamps, okay? Again, the phase A is 0 kiloamps, that was expected. Phase B, 14.25556 at 150 degree, and this is kiloamps. And finally, for phase C, we have again the same magnitude, 14.25556, and the phase angle is 30 degrees, and this is in kiloamps, okay? Okay, this is the way to solve the problem if you don't think outside the box, okay? If you think it that way, okay, yeah, you solve the problem. Good. However, I always try to make my students think outside the box, okay? And in this problem, there is a very interesting property. And not much people think about data and think about properties when they are solving problems in mechanical ways, okay? If you look the data over here, let me go back to the data. Let me minimize here. As you can see over here, positive and negative sequence, they are equal. Okay, that can happen. Positive and negative sequence, they are equal, and they are equal to 20%, okay? But in this problem, we have a very specific neutral reactance, and when we convert that into per unit, there is something that is happening that is quite interesting, okay? If you look over here, let me remove this in order that you can see the numerical results, okay? If you look over there, in these three lines over here, you can see the positive, negative, and zero sequence, okay? If you look the positive, negative, and zero sequence, the equivalence, of course, because over there we are including 3 times the neutral reactance in the zero sequence. I believe that all my students, they can see a beautiful property that happened there, okay? What is the beautiful property that is happening there? Something that is not quite typical, but can happen. And in this case, this problem was designed to happen. And in this problem, what is happening is that the positive sequence, the equivalent positive sequence, equal to the negative sequence and equal to the zero sequence. All of you can see that that is 0.2 J, okay? Okay, that is something that is happening only in this problem. But when you have that very specific situation, the calculations that you are doing more calculations than the calculations that you need to solve the problem efficiently. Because when you have positive, negative, and zero sequence, all of them, they have the same value. The solution can be simplified and can be done in a simplified and faster way, okay? And that was what I was asking to my students to reflect about. And that was my original idea behind this problem, okay? Now what I will do is I will solve this as I was planning to solve originally, okay? What I will do now is I will minimize my MATLAB script, okay? And now what I will do is the following, okay? Let me take a white piece of paper and I will come back to my problem. Let me put back here, okay? And now what I am showing you is the original problem, and now I will show you a very interesting way to solve this problem, okay? What I will do is the following, okay? First step first, we will do something similar what we did before, okay? What we will do is, initially, what I would like to do is calculate the impedance base. And you must remember the values that we calculated before is the square value of the nominal voltage divided by the total MVA, 3.22 ohms, okay? Something that I would like to fix over here is that now we need to calculate the neutral reactance. This is the neutral reactance, okay? This is the neutral reactance. The neutral reactance in per unit values, okay? How do we calculate the neutral reactance in per unit? Well, it's extremely simple, okay? What we need to do is, if we want to calculate the neutral reactance in per unit, is dividing the neutral reactance by the impedance base, okay? And dividing the real values is given 0.162 ohms, and the base impedance that is 3.22. This is the neutral reactance in per unit, okay? Simple. Next step. Okay, now what we need to do is calculating the zero sequence, equivalent impedance, okay? Because this generator is connected at a start connection and there is a neutral reactance, that means that the equivalent impedance is the zero impedance of the generator plus 3 times the reactance that is connected at the neutral point, okay? And here what we are getting is the magic, okay? Now you can see that here is the zero impedance equal to the positive impedance equal to the negative impedance. And all of them, they are 0.2 J per unit, okay? Beautiful. Then next step. Well, next step is extremely simple. Before the short circuit, the generator voltage was adjusted to 16 kV. 16 kV is different to the rate voltage, 18. We calculate the per unit value. You can see here the per unit value, 16 kV divided by 18 kV. We get over here 0.889, okay? Then I did something quite interesting over here, okay? I did something interesting quite here. What I did here is, okay, what is the line to ground, what is the line to ground fault current in this situation? And you are wondering, okay, what is doing this guy? Because this guy is solving a line-to-line ground, but he is using here the positive sequence coming from a line to ground, okay? And you will say, okay, no, but if you are using line to line to ground, the positive sequence current should be, because you must remember, okay, you memorize the equation, and the equation is equal to okay? And you say, this is ground? No, this is ground. Okay, give me 5 minutes of faith. And then you will realize that this problem is magic because this condition. Okay, what I will do now is, let's do the following, okay? What I will do is calculate the positive sequence currents, but based in a line to ground fault, okay? If you can see over here, they are in series because when we have a line to ground fault, the 3 sequence networks are interconnected in series, and you get here the sum of those quantities over there, okay? Now you are with me, okay? And then what is the current that we get if we are applying a line to ground fault? Okay, well, you must remember the fault current, if you are having a line to ground fault, is 3 times the positive sequence. And if you multiply one, sorry, let me clean my screen, okay? 1.48 1481 3 times. Wow, look over here. 4.444. Come on, what is happening here? This number must be familiar to you because if you remember, I use MATLAB code. And I use the proper calculation using this equation that we have here for the line-to-line ground, yes? You must remember that I use that equation. And when I use that equation, the numerical results, look over here, numerical result, 4.4, periodic. And when I use this equation, I got phase B equal 4.4. But when I use the line to ground fault, I calculate the positive sequence and then calculate the single phase current on phase B, and I obtain the same per unit. And if you use the base, if you calculate the base, no problem at all. Look over here. Let me put it this way. Yeah. If you use this equation over here, 14.25556 kiloamps. If you use this equation for single line ground to fault, you get 14.254 kiloamps or 14,254 amps. Okay? Conclusion. And if this situation is happening, positive equal to negative equal to 0, if that situation happen and you have a line to ground fault, that short circuit current in phase B will be equal to the line to ground fault current if you have the fault on phase B. Yes, this is magic. When I first showed this solution to my students, I say, reader can demonstrate, and then I put this equation over here. And nobody believed me. Many of my students come back to me and say that is a typo. And of course, because I have so many typos in my class notes, they come back to me and say, no, you are wrong. Okay, now I record this video and I am showing you that if you have a double line to ground fault in a system where the positive, negative, and zero sequence has the same impedance, the current in phase B will be equal to the fault current if you have a single line to ground fault in phase B. Okay? Okay, my dear students. I say my students over here, reader can demonstrate. They come back to me and say that is a typo. And instead of trying to demonstrate if that is true, okay? I say here the very important conclusion. I put here this very important conclusion as clarification for my student. Reader must demonstrate that if the power system sequence happen to be equal, positive, negative, and zero, but the fault current of a double line to ground is equal to the single line to ground, okay? I say that this is the key. Double line ground faults are equal to a single line ground to fault, okay? But that is only happening if this condition is true. If that condition is not true, okay, go back to your equation, go back to square one, start to do your calculations, okay? Okay, sometimes students, I put this and they don't want to go to equations. What I will do now is make a very short demonstration over here, okay? Sorry, I didn't went through all the calculations, but if you are having a double line ground fault, if you are having a double line ground fault, yeah, double, let me put bolts over here. If you are having a double line to ground, this is the equation. My student memorized this equation for the positive, for the negative, for the zero sequence, okay? Good, simple. And then what is happening is something simple. This is what is happening. If the positive sequence is equal to the negative sequence equal to the zero sequence, okay, this equation is simplified because negative and zero sequence, they are the same. We get this one. And what's happened if in this equation, if zero sequence is equal to negative sequence? Well, it will be one set here, two set here in the denominator, negative at the front. You get this, you get that. Yeah, you can do that. Okay, and then what is the next step? Okay, the next step is let's use symmetrical components. And if you use symmetrical components, what you need to do is, okay, this is A, B, C. This is the matrix A. This is the symmetrical components. And what I did is I only substitute the values that I got before. What I'm trying to say is what I did is I0 is equal I0 is equal to minus half of I1. Negative sequence is minus half I1. And then what I did is I1 is equal voltage previous to the fault. Yes, you must remember from here, twice the voltage pre-fault, twice the voltage pre-fault divided by 3 times the positive sequence. Okay, that is what I did. Then I apply here the property of the matrix A. I multiply, I simplify the equations over there for you. And what is the final conclusion? The final conclusion is, as you can see over here, the current in phase B is equal to this number. Okay? Is equal to this number. That equation, okay? The voltage previous to the fall minus the voltage previous to the fall, half divided by positive sequence multiplied by 260 degree, okay? And then what I did is the following, okay? I can compare with the single to line ground. And the single line to ground is basically 3 times the positive sequence, okay? 3 times the positive sequence. And if you use 3 times the positive sequence, but this number is equal to this one, what you will get is 3 times divided by 3, they cancel between them, and you get this. And that is numerical equal to the magnitude of this. That is simple. Again, the conclusion here, The very important key point is if we have positive, negative, and zero sequence, all of them, they are equal, in that system will happen that the magnitude of the fault current of a double line to ground will be equal to the single line to ground. Okay? Well, I hope you can see that it's very interesting when you are solving problems that first stop, see the properties, and see alternative ways to solve the problem and alternative way to save time. Time is extremely important. Time is a currency. Please try to use your time efficiently, especially for exams. Okay. Well, I will not spend so much time. Um, Probably some people will come back to me and start to make me question about this mathematics. Okay. Again, I don't have so much time. Again, time is a currency. And what I need that you understand is there is a demonstration here that I did using symbolic mathematics inside MATLAB. It's very simple. I say the reader must demonstrate that if positive, negative, and zero sequence happen, what is the values of the currents I, B, C, okay? And what I did here, you can see over here, I defined several variables as um, symbolic variables. Then I define the operator A. Then I say that the negative sequence is equal to positive. Then I say positive, zero sequence is equal to positive. Here is the formula that my student remember when we are using a double line to ground. But in this case, because we are using double line to ground, I make here that the positive and negative are equal. And you can see here that the positive sequence will be 3 times divide by 3, 2 times multiplied by, divide by 3 here. And then I calculate the negative sequence and zero sequence. Then I use the matrix A. And those numbers that you are getting here, the current for phase B and current for phase C, that is what I am showing here, okay? Look over here. You can see that this is the value coming from the phase B. This is the phase B, and this is the phase C, okay? Finally, to close this problem, what I will do is the following, okay? I will come back to the original solution, okay? If you remember here, I use the proper equations. Yes, remember, we use the specific equation for the double line ground to ground, yes? Double line to ground. And, and what I want to show you is, okay, what if we calculate the single line to ground, okay? Okay, and then what I did was create another MATLAB script, of course. And over here, let me show you the MATLAB script. And in this case, I will show you the short way, okay? The short way is very simple, okay? It's almost the same code. We have here the positive and negative sequence. We have here the zero. We have here the neutral reactance in ohms. Then we calculate the impedance base. Then we calculate um, the reactance, neutral reactance in ohms. Then here, what we are doing is calculating the reactance. As you can see, the property is evident over here. Positive, negative, and zero sequence are equal, okay? That is the property that I was discussing as the core of this solution, okay? Then what I did is, okay, let's calculate. This is a line to ground. This is a line to ground fault, okay? But let's calculate the positive sequence using a single line to ground fault, okay? Let's calculate the current using a single line to ground fault, okay? If we use the single line to ground fault, There are no surprises. The voltage divided by the sum of the three reactants, because if we are using a single line to ground, positive, negative, and zero sequence, they are in series. Then what I did is, okay, this is the positive sequence. Now let me calculate the fault current. And you must remember that for the single line to ground, single phase to ground, we have that 3 times the positive sequence is the fault current. And look over here, let me run the simulation, and we got this result over here, okay? Now let me compare with the results when we are using, let me compare with the results when we are using the full model, the this equation over here. If you remember again, if we are using this equation, the result is 4.4, yes, per unit. The only difference that I say to you, and I was very clear when I say that, is that the magnitude of the double line to ground fault is equal to the magnitude of a single line to ground fault if this condition happen. I will tell you again, the magnitude of the double line to ground fault current is equal to the magnitude of the single to line ground fault if this condition on the impedance, positive, negative, and zero impedance are equal. And as you can see here, this is the per unit currents when we calculate the double line to ground fault. And here below, you can see the line to ground fault, and the magnitude is equal 4.4 periodic 4.4444 per unit is the current. Now the phase angle, okay, that is another history, okay? That is another history that I will not go here, but please be aware that this example was created in order that my students reflect about this kind of conclusion. What's happened if the three impedances, sequence impedance, are equal? Okay. Well, I hope you enjoyed this video. And again, this very specific example was created to reflect about properties of power systems based on the sequence impedance. Okay. I hope this video clarified many things. Probably not. I'm not so sure. What I suggest is download the MATLAB scripts, go through the code, see the numerical results, and reflect about them. And then you can see that it's extremely simple, and what you need to do is understand properties about power system, okay? Again, teaching engineering is not easy. Teaching engineering is not teaching equations. Teaching engineering is teaching how to think in order to solve problems. It's beyond an equation. It's beyond a single equation and putting numbers inside. Okay, well, thank you very much to all of you. I am sorry that this video was so short, so long. And also, please forgive me if you still confused with my explanation. If you don't see this at the first, probably you will need to spend many hours trying to see this. And even with my best explanation that I try here, you will not see this. The only way is that you realize that you understand this by yourself. Looking into the equations, looking into the demonstration, looking into the numerical results, and then everything should be clear. Well, that's all for today's video. Thank you very much for watching. Please keep subscribe to my YouTube channel, and see you around. Thank you. Bye now.